involved in Emerson. I'm based in Stockford, Texas.
Okay, so this presentation was the second presentation. I think you already have seen some of Emerson's presentation, but just to show you 100 years company very embedded under this process. So I work specifically, like I said, with the wireless, but for sure, and all the wire instrumentation is widely spread in the processes. And well, here's also our commitment to the sustainability. So top down at Emerson. So not just what we can offer to customers, but also what we do inside as well. Website with our Czech Sustainability Officer for details on our initiatives. Okay. So let's talk about the PRV monitoring. So this is we present this material yesterday. We're going to be a little more specific today on the monitoring part, but I just want to talk about this slide briefly about the affirmative. So, which is basically a way that when we have an incident, now we need to discuss with the regulator. So, how we're going to position your claim? So, well, what I can should include in my claim or not, right? And but what we're seeing, and this is a copy of the administrative code from Texas. Like we took Texas just an example. But well, when you can invoke the affirmative, right? So when you have, say, equipments, break of equipments that for some reason those say so old or obsolete technology, and you don't have the replacement parts, yeah, you can claim or use the strategy for affirmative defense that you could not make a correction because, well, you had some parts or equipment that was not available, so was above your control to do that repair. Anyways, in other unplanned events, etc. But if you read a administrative code like that, so the regulator always is going to check your historical about the good practices for minimizing emission, right? So what else is here? Prompt action, pollution control equipment, amount of duration of each event, okay? So documentation, okay, how frequent that was. Okay? So then this is all the little items that the regulator will check to see if you're on top of that, and if your claim was legitimate, right? Is really related to say, this is out of my control. So what we're going to cover here is an important portion of that, that's the PRV, because if you do your homework with the PRV, you're going to be able to check, mark, and all of those things, and not make that as something going against you when you are claiming the affirmative defense as your strategy to minimize that discussion with the regulator. All right, so with that, I'll let Marcelo.
Thank you, Marcelo. So I guess the point is, what's the connection between PRV and affirmative defense? And I think the connection is there are first, if a PRV goes off, it opens. It's not a problem with the PRV. It's actually a process. It's a symptom that your process is overpressure. PRVs are not supposed to open. They're actually designed to close all the time. If they're open, you should investigate. There is a problem there. So it's by definition an expected event. So it clearly check the box is unavoidable. It's an expected event, it's beyond control. Something happened there. And there are what we're trying to say is in this presentation is using digital transformation. There are there's existing technology that you can use today, implement that you can really build a strong case. Okay, I know PRV is not supposed to open, but I'm monitoring when it happens. So it's not the case that the valve opens and stay open, people don't see, or the valve is leaking and you know the valve is leaking. I can monitor that, and you can build a case if there's. And there are other things we're going to show around. So it's using existing technology and the benefit of digital transformation to build a stronger case for affirmative defense. That's the context. So going back to the PRV 101 school, for you, if you're not familiar with, they are designed and the proposal of this, we call it the last line of defense. So when everything fails, if your control system fails, your VCS, your emergency shutdown system fails, the PRV is going to work. It's going to shut down, you're going to release, you're going to protect against explosion, people, equipment. That's the definition of how PRV should work. And they are designed following a lot of codes and legislation, local, county, and there's insurance companies that play that too. So it's a safety device. If everything fails, this stuff needs to work. And by definition, it's very highly regulated. It's super simple. Nothing's, you know what's a pressure cooker? That's it. You know the stuff that goes, that's a pressure relief valve. And the compromise that is safety against what? Waste. When you release, you're throwing things out. Energy that you do not need, just throwing out. Product that you're throwing out product energy and efficiency when you open a pressure relief valve. You're compromising. Keep that in mind. That's very important. And it's a simple device, super simple. So if the force that's going resulting from the overpressure in your system is bigger than the spring force that's been keeping this closed, this thing is going to go up and it's going to release. It's very, very simple device. It's designed to be simple because it has to be reliable, and it's not connected to anything. It's mechanical. It's purely mechanical device. So it's designed to be there, and normally you will never pay attention to that until you have a problem. That assumption is, it's there, it's not doing anything, so it's not really, I don't need to mess with that. And people are actually afraid of going close to that, right? That's the reality. And another interesting point is, this is a device that's supposed to never work. If your process is working well, they shouldn't open, right? By definition. So if they're not going to work never, you don't have any way to diagnose it because they're not connected to anything. How do you know it's going to work when you need it to work?
Yes.
Preventive maintenance. Exactly. And that is exactly the golden standard that we do today. Preventive maintenance, we do every 2, 3, 4, 5, 6 years. We have an interval that we test the valve. And that is by definition disruptive, because you have to remove a valve. You cannot really run your process without a pressure relief valve. There's a lot of, it's critical for your process availability. There's a lot of implications. So you use preventive maintenance at pre-scheduled intervals to keep the availability of the safety requirements of your process, because the valve will work. But there is a compromise that you have to shoot on your process. Another interesting point about pressure relief valves, they're the most valves to access. They're on top of everything. So people talk about, let's do a walk down. Don't do walk downs with PRVs. You climb everywhere. It's a very labor-intensive risk assessment. And the challenge we have today, the new regulations for safety and environmental, they're requiring you to check if the valves are operating properly, if they are leaking. or the open. And how are you going to do that? You have to go there, climb with a sniffer or check or sound or whatever, and see if the valve is leaking or not. Or some people even put their hands to discharge pipe to see if it's hot or cold, to see, oh, that's a lot, valve is leaking. So it's very, very challenging and risky too. Personal safety. And more requirements to do that. Another challenge is if you need to do a check, a test on the valve, you have to remove the valve. We did a study, it takes 4 man-hours per valve to remove and reinstall the valve. 4 man-hours. And that's not counting any time you spend at the valve in the shop doing the real test, just to remove them to the valve. That's the average for chemical petrochemical refining companies. If you need scaffolding or crane, that multiplies by 2, 3, or 4. And if you're in the middle of a turnaround or a shutdown, you have to do a crane. You need to ask a crew to go there and then get permits, and then it really disrupted time. It disrupts the entire thing. The bottom line is if you could understand and have a way to reduce the frequency and use more intelligence in the way you do maintenance on those valves, you'll be better served. You could definitely improve your efficiency, reduce costs, and improve safety at the same time. And that's the kind of the core of the value proposition for monitoring and using digital technology on PRVs. There's a little more. We actually did a study with 10,000 service records on the pre-test. Right? Pre-test is a common exercise on PRVs. So if you have a valve in the field, then you go on one of those 2 or 3 or 5 year intervals, you bring the valve from the field, you put it on the bench test, and you do the pre-test. The pre-test, you apply the pressure that the valve is supposed to open. Let's say it's 100 psi, you apply 100 psi in the valve. And you see if the valve pops, because that's to guarantee the valve is going to open at 100 psi. That's the basic. Remember how we do that? You're probably familiar with that. But, so the data we got from 10,000, and you have to record what you found. The data we got is pretty alarming. This is a top quartile refining petrochemical complex in North America, one of the best running in the world. And the data we have is 20% of those valves will be leaking in this pre-test. When you bring the valve from the field, as is, that will be leaking before you reach 50% of set pressure. So if the valve is 100 psi, you apply 50 psi, the valve is leaking. The majority of the valves are installed above 50%. You know that you want to go as close as possible to operate above 50% of set pressure. This suggests that there is a large population of valves in the field leaking process all the time for 2, 3, 4, 5, 6. We don't. The question is, when did it start to leak, and why? There's no way to know because they are not connected to anything. Unless you monitor. Exactly. And if you're lucky, right, when you open the valve after, the valve is leaking, let's open the valve, and you may go there and see a scratch like this that suggests that your valve popped in the field because it was an overpressure event. That's not supposed to happen. But nobody recorded, nobody saw anything, right? But it did happen. And reclose, and the valve scratched, the valve is leaking. It is, we know when you size a pressure relief valve, we know why valve open, right? There are a series of scenarios that you go through to size how much capacity you need to keep your system safe. And some of those scenarios are, block discharge, overfueling, thermal reaction, and blah, blah, blah. There is one though in the bottom here that we cannot control, we cannot size for, its operation changes. I have talked to operators, I have seen this happen. And what happens from shift to shift, an operator may, so this valve is set for 100 psi. But I can operate it at 90 psi. That's no problem. It's 90%. That's okay. Pressure in valves at 90% of set pressure, if they are metal seated, they are going to be simmering. They are designed to start to simmer at 7 and 90, which is going to mean and that is leakage. So you're passing product to that, you're scratching the surface, and that's happening. People don't notice that. And then the next shift comes, they reduce the pressure, everything's fine. No. Problem there. And what's the number, Marcel? It's, I think, at 0.1% leakage in a valve equates to a valve open for 6 hours for a year. If you have a valve 0.1% leakage, it's a very thin leakage, right? For 1 year, of course, you don't know. There, it's the same volume of a valve fully open for 6 hours. Can you imagine if you fully open for 6 hours, how much you're going to throw the product or the atmosphere? So it's a lot of volume there, because those are high pressure devices. Anyway, and in this graphic here, what we have, well, everything I told you is about history. This is real online data from one refinery that installed those sensors, and they get a data. And this device Marcio's going to talk about is an acoustic device, the Rosamond 708. It has 2 sensors, one temperature probe and one acoustic sensor that we install in the discharge pipe. So you can measure when the valve opens or the valve closes, and you can measure the temperature of the discharge pipe of the valve. And here we have 2 signals. So the customer had installed, they got this graphic, which has a temperature plot and an acoustic signature plot, which is the vibration of the pipe. He couldn't understand, I don't know what's going on. Called Marcio, right? And Marcio called me, we talked about the valve is leaking. What happened here is very simple. You have here's the temperature is here. The blue line is 0, which means the valve was closed. And then you have a relief event, the valve open. The temperature rise at the same time, which is, confirms that the valve was open. Then the valve reclosed. But look what happened afterwards. The temperature did not return to the same level, and there was a bias. And they had another relief event afterwards. And the customer was oblivious, and he didn't even know that they had a relief event. It was graphic that showed. And that's what happened. The valve had a release event, and then started to leak, and that's it.
Well, let me just do
Yeah,
a short comment here. That was interesting here in this case. Just a little.
Almost.
This interval here is 1 hour, so about 6 minutes release. Then the valve, obviously, well, the valve did what's supposed to do, right? So it depressurize the system. So here's the region that the system was built up pressure again when reach out to critical pressure.
Operating pressure.
Yeah, operating pressure. Boom. Here's the signature of the leakage. Well, the leakage could be just as simple as a debris blocking the valve. That's one of the most common. This case here, because we have a second, same pattern, same level of leakage, so now it's becoming too suspicious. It's too difficult to be same size of debris, right? Well, yeah, so we had this valve inspected, and it had a mechanical damage. So the stem, so it was permanent damage. So that's the power of the monitoring. Because just monitoring, like I said in the previous section, it could be your worst investment. So you needed to use monitoring and then take the action. So the action here is saying, wow, we're comparing 2 things, and then they took the decision, well, this is not a trivial leakage because this is a permanent damage, right? So yeah, this is a real case.
And there are others,
Yeah,
right?
yeah.
That we molecular over the years. And what are the implications? Well, it's one of the few applications that touches a lot of KPIs. It touches emissions by definition. As I said, it's a compromise between safety and release, emission, energy, everything going off, right? Yeah, I have either goes to a flare, which is not good, or goes to a recovery system, or goes to the atmosphere. That's bad. Another one, production. It's energy you're throwing out. Another one, reliability. If you're over pressurizing your system, you are definitely wearing your system more than it should mechanically. Other parts, not just the PRV. The PRV is going to damage because it's not designed to be open and closing all the time. So we're gonna have a shorter lifetime for this device, but other devices in your system probably won't wear and tear more. And safety too, because if those examples when they both open and close and it's okay, yeah, it's gonna be leaking bad, but at least the valve is operational. But there are scenarios when the valve opens and there are non-stable scenarios that you can have a valve fail on the bad point, which is the valve is not going to open on demand, and that is and you don't even know you have that. You have a PRV valve that may not be operational, and you do not know, and that is not good. And we have plenty of cases where bellows crack, for example. It's a very common event because the valve went to rapid cycling, for example, which is not supposed to happen. And then you just, the valve is not as safe as well. So we'll talk about that. So it's not a good point to have pressure relief valve leaking all the time or opening and closing all the time. And the beauty of monitoring pressure relief valves is if you have an event 2 a.m. last night, oh, my pressure relief valve opened 2 a.m. last night. Oh, wait a second. I can see that. What's the pressure in the vessel? I can correlate the pressure relief event with the pressure in that vessel, with the temperature, with the pH, whatever is around that are the real causes for that valve to open. Because the valve is the symptom of your problem. The problem you have is actually an overpressure event. It's a process problem. And you can troubleshoot your process. You can design a much more robust process. You actually can make money for a better process because we have cases, documented cases that operators made an investment, and it was an environmental investment and made more than $1 million in operations production because you can understand your process better. And that's a different ballgame. You can redesign your process based on this. You can map your problem. And let's not forget, a pressure relief valve going off is a near miss safety event. Unfortunately, we're not recording, but it is. Because if that valve was not there, you have a problem, your vessel would cause a catastrophic event. So, and that is a safety part that is not well explored yet. And Marcel, all yours.
Great. Yeah, so challenges, right? With the how we're going to monitor those PRV, right? So when we think about PRVs, in closed system, what the regulation wants to know, or the regulators wants to know, is where this flare is coming from. What's the bad actor? And we have a bunch of PRV discharging to the flare headers. It's really difficult to make. Well, with the one that is released to the atmosphere, it is also difficult, but yeah, you can have some clues, but not when we're in a now, one thing that say EPA, they're okay if you correlate pressure from the process and kind of tie that up with the PRV. They're fine with that. There is a problem was a drop of pressure, process pressure drop. It could mean hundreds of other things. It could be a PRV that was released. It could be many other things. So the big challenge is, okay, so doing the deep diving on your database and starting unselecting or proving that, oh, there was not this, there was not that, there was not that, that could take weeks, months, or maybe you not even know exactly what was the real cost, right? Manual rounds, well, that's a classic case. Have a release, but we have manual rounds, say 8 hours. The best that you can tell PA about the events is before the round, before the event, and after. So maybe the event was 20 minutes, like we show here the other case, but you cannot prove you're gonna be charged by the 8 hours or whatever between manual rounds, right? And the last thing is wiring. Think about, say, cost per foot is about $100 installation cost per foot. Imagine all those PRVs in this weird location, top of a vessel, etc. So the investment in wiring is just out of the charge to justify those kind of products. So that's where we came up with the challenge in our engineering group and say, well, we needed a solution for this problem, right? And here's the chart. So the slide, we have a typical spring load operated PRV. And okay, so we understand the challenge. Using the pressure, system pressure is not a good idea. So what we can do? So if we cannot monitor the inlet of the valve, right? Or the only alternative is to monitor the outlet. For the outlet, we have another problem here. This little piece of a pipe is heavily regulated. Okay, so you cannot have penetration, you cannot change the dimension. There are some complications here. So the way to go here is using something that's non-intrusive, something that we need to tank in the pipe. And the answer to all those questions, they came through using acoustic transmitter. So when we say acoustic transmitter is not something that this is wave propagation, mechanical wave propagation in the pipe. Okay? So loudness in the environment, the surrounding environment doesn't mean anything. So you're not able to use this as a microphone, right? This works in a low ultrasound frequency. Okay? So that's the idea. So use it as a acoustic transmitter. So as fluid pass through the pipe, it will cause this vibration, and the acoustic transmitter will recognize that vibration and will transform that in electrical signal. Okay? And as Marcelo said, also we have a temperature monitor. So we use the two variables. And we have this demo, a real demo on the near the area. So we'll be more than happy to do a real demo. So it's a PRV that's pressurized 40 psi. So we're not gonna. EPA doesn't need to come here. So we can play with that, and you can experience, or you can see the technology and test the technology. Now, there is another category of PRVs. So the pilot, the spring load is the most common, most frequent. There's another one that is the pilot operated PRV. Okay, so the spring load with acoustic. We know when the release occurs, when it starts, when it stops, its duration, exactly like the EPA is asking on the regulation. That's the word that they're using. Not with my accent, but believe me, that's the words that they're asking. We can have a very good idea if this PRV have a small leakage, medium leakage, but we cannot quantify using that. It's just like that. We cannot quantify. Which it's okay for the most cases, because honestly, the bottom line is you need to understand when the release happened and then take the action. Just start calculating your losses. Yeah, this is not the point. But there will be a case. Yeah, you want to know what's the volume that we're. So during that point, the recommendation now is upgrade to that PRV, not from spring load, but we're going to use the pilot operated PRV. And then the pilot operated PRV can come from, if it's Emerson pilot, can come from factory with a transmitter that we're going to tell you what's the flow that's passing through the. So basically, we can quantify the flow passing through the.
The pilot valve
Yeah.
has the characteristic of being like a regulator, so
Yeah.
it doesn't pop 100%. It can go just 10% to stay there for a minute, 10 minutes, forever, just enough for so. And there's a big difference to have a valve to report 10 minutes at 100% and 10 minutes at 10%. So that's so some of our clients are buying this to put in their pressurized tanks because they can quantify the better level. And we have the area, we have the differential pressure, the lift, we can calculate it.
What's the metal that you use? You have nickel, you have stainless.
Oh, everything. Stainless for the transmitters and the valve, everything. Ever all the way.
Okay.
Like then. So that's
Yeah. So, but anyway, so when we say PRV, we always think about the spring load, but yeah, pay attention that this is wonderful technology here for PRV that's pilot upgrade. In many cases, is worth the upgrade, and you have something that's not popping, but proportional.
there are two types. So it's a high pressure pilot that's used for, and there's a low pressure pilot on the right that's normally tank or LNG or natural gas or.
Now, who does not know Steve Gross here in this audience? Anybody that does not know Steve Gross? Yeah, this is a popular. So we took Steve Gross for a tour at the plant facility that Marcelo works involved. And yeah, he was absolutely surprised, amazed with all the technology that we have with the Crosby, Anderson, Greenwood, etc. Then we show some, Steve, look at this thing here. This other product. It's not the PRV, right? And everything that he was excited, just to put that in the back pocket, and it was really crazy about this thing here that we call the safety. So Marcelo,
about that.
yeah. So tell me more
It's
about that and why
the function is
Steve
super
was
simple.
crazy.
It's like if you have a valve, you put this device and you put two valves, one backup and the other. And the point is, as I said, if you remove PRV for maintenance, your process is down. Now, if you have a backup, you switch like this, and you can remove the maintenance, or you can continue operating and plan your maintenance, but your operation is up and running. Now, what Steve foresaw was, wow, this is a great case for affirmative defense, because if I have an event and I'm monitoring and I see that the valve is leaking, I can document it because I'm monitoring, having that data, and I can go then and switch the other valve, and I can tell the EPA, by the way, I did my action. I had this unexpected event, was this release, there was this leakage, and I went to the field and switched the other one. So it's kind of the best engineering practice.
Yes.
You get some super strong case. That's his word, right? So
Yeah.
and you can do this for open atmospheric, or even if you have a closed system, you can put it in the tendon. So you can that's the combination of this is a 30-year, maybe 40-year technology that we use. And it's a lot better than using a ball valve because the flow is minimal losses, which is very important for the safe operation of pressure valve. And this design is called safety selector valve.
Yeah,
But
we
it-
have similar three-way valves, like the ball valve, but the three-way, you know, it goes to one or the other.
Yeah,
Not on all our equipment, but some.
yeah, and critical for availability,
Yeah.
exactly. The difference between a three-way, if you want to take a look here, is the net losses that you have, especially valve. So, of course, if you have like, let's put the valve supposed to open at 100 psi, right? When pops at 100 psi starts to flow, if you have too much inlet pressure losses, because there are too many curves to get there, you're going to lose pressure. So the pressure that reaches the valve is not 100 anymore. You have 100 at the tip, it's going to drop to 95 or 90. Then the valve is going to reclose. Then builds again, open, and close.
Yeah.
This is going to destroy the valve. Pressure is a matter of the valve.
So it's really engineered. It's not just a game selector switch. It is designed specifically for PRV, pressure compensation. So anyway, so it's basically is kind of dreaming to come true. So yeah, it is possible replacing PRV without putting the pressure. It is possible. It's tangible to maintenance PRV. Cycles.
Not cycle.
How many cycles?
Well, I mean, Those
Cycles on this?
Yes.
Before it starts to leak.
Uh,
The seat, imagine the seat will start leaking on the block end.
in this?
Yeah.
That's a good question. I don't have it. But you're not supposed to be cycling this multiple times, I guess.
Well, I mean, yeah, I was just wondering, obviously, you don't want to replace it every
No,
time.
you
because-
don't, no.
Because that defeats the purpose, right?
No,
So
it's,
you would want to know how many cycles I can
it's-
go.
I don't have a top of my head, actually, but it's being used for more than 30 years. So, if people use all the time for maintenance, it was never envisioned for this scenario that Steve came up with. People use this a lot for availability and for installation.
So I told the knowledge to go here. The cable is completely out of the any possibility to justify projects. So the way to go here is using wireless technology because we're monitoring, we're not controlling anything. So when we're monitoring, the wireless is the right thing. And it's very common. You have already in the when you say wireless, is a very specific protocol called wireless HART. This is a industrial protocol. When we're talking wireless, we're not talking cellular communication. We're not talking 5G. No, this is a very, very specific wireless technology. And for a small package of information, highly protected, multiple redundant paths. So there's a lot of halos around the industrial wireless communication that differentiate what it's our normal experience with access points, those kind of things. Okay, so then the idea is having the PRVs all in the wireless heart. So next, please. So then this information from the PRV is going to reach out gateway, which again is very possible that we already have this gateway in your installation for some application, but these gateways, wireless heart gateways, they are mix and match. So yeah, you can use for your PRV, but let's say somebody on the reliability already installed this gateways because they're using for their pump monitoring, whatever. But yeah, you just use the investment that you already have. And then from here, traditionally, we send this information to DCS. Okay. But now we're changing this the way when we're doing this with an analytic software. So we have an analytic platform that's called PlinkLab Insight. So PlinkLab Insight basically, it's going to 5 minutes. We have this PlinkLab Insight that's gonna collect all this information from the PRV, and we have a app for PRV specifically, and we'll say, well, that's what we call, we're gonna characterize all this information from the acoustic signal. We're gonna make the distinction if there's a pulse positive, not pulse positive. What's the natural vibration of the system? What is a real release? Those kind of things. Okay, and we're gonna produce data that will it will match with what EPA is expecting. So when we were putting the idea here with the ZAC, well, yeah, we took the EPA consideration, what they're putting in their regulation, and said, well, let's give this to our customers and our community, right? So, yeah, this is the typical screen, and then the alerts, and then have alerts for not just for environmental, but also for maintenance. So it's not a system that, yeah, we can make more departments happy with that. It's not just a same for anyone. Okay, let's go ahead, Marcelo. Okay, no, one last, well, rupture disk, that's another kind of complementary technology that we needed to use with the PRV, right? So especially in the special chemicals. And again, so we have a specific app monitor the rupture disk and send all the alarms as well. Everything more or less. Okay? So no more wires. Yeah, and this is let's just go more into detail how we avoid this knowledge. Could be in a central station, could be in a server, could be even a cloud if your corporation has a cloud. So then you can multiple sites. You can optimize the expertise. So you have one expert taking 3, 4, 5 planes. Yeah, well, with the system, yeah, you can share all the information by planes and then optimize your SMEs.
Some examples.
Yeah, and there's some examples. You're going to be able to access all this information website. Then you can take a look.
I think this is not the latest.
Huh?
It's not the latest.
Okay. Oh, it's working out. Yeah.
Yep. Go ahead.
Yeah. Okay. Yeah. That's it. So now we're end up with our presentation. Questions?
The battery life.
Yeah. It can vary from say 3 years to 10 years.